Okay, hello everyone. My name is Marjorie, and I would just give a rundown of the Titanic DevOps assessment project that I worked on recently. Increase my volume a bit. Okay, so the project did provide a source code, which is basically a Python Flask API. And the task was to build the Docker file, Docker compose, testing, and deploy on Kubernetes, provision via Terraform, and configure monitoring and observation while considering security at all stages and document. So I started off at the application source code. We went ahead to write the Docker file. We do have two Docker files here, one for prod and one for dev. This is for prod. The basic difference is the prod will produce a slimmer image. The base is it's slimmer, and what else? It's going to ship faster in production. And then we did build the image. We had test and deployed with Docker Compose locally and opened a local host at port 5000, and we got this, right? And here's the Docker file for Docker Compose setup, right? And we moved next into, okay, the task did have some specifications to ensure that to ensure some security best practices like no root user. So we do have the app user here in, running the Docker file. And yeah, I did have a bit of some issues, but you know that as we progress. Moving on, I went next to the continuous integration and deployment of the application. It started off with the branch strategy here, where the workflow triggers on push to all branches. Mind you, we're on the dev branch, and pull request to main and manual deployment with these specifications as declared here. So we included these because it also has the deployment, continuous deployment here as well for various branches, and includes rollback strategy, right? So the first day, okay, we do have some variables declared here, environmental variables. All right, and then next, so we started, the first job started off with a run, a git scan run, which basically called this action from a different repo. The reason for this is sometimes, although this is a single application project, but in a real world situation, we will have several microservices that will have several CIs, and rather than install packages on each CI, it's usually faster and easier to call certain actions from a reusable repo. So that's what we did here. We did call this git scan action from this repo. Yeah, it came up on my other screen. Okay. So that's it here. All right. So these are the actions we are going to be calling in this UI: the check-off scan, JIT-leak, SonarQube, and Trivi scan. Right. So this job is going to basically going to stop the pipeline should it detect any secrets leaked in the workflow. And the next job is where is the tab? The next job is the checkup scan, which is actually an ISC scan. It's going to scan the Docker file for CVEs, irregularities, and all those. It's also going to fill the pipeline if any CVs are found or incorrectness. And we're moving next to the unit test and linting coverage. For this, it's a Python-based application, so we had to install basic dependencies and packages to run the JIT-leak, to run the Python unit test. And the reports, including the coverage and all, was loaded into GitHub Actions as an artifact, which can be recovered for other use, or rather later use, and then move to the code quality SAST scan, which is basically calling the SonarQube scan from the reusable repo. It's going to use the SonarQube token, which we generated at Sonar Cloud. And okay, I didn't mention the unit test. What it does really is to check for functionality of the code, right, as a unit of that microservice, right? And the SonarQube actually should test the functionality of the units put together as a whole. Yeah, but it is what it is in this case. And what is going to test for bugs, duplications, and any other irregularities. And if it passes a set quality gate, the workflow continues. But if it doesn't, it does stop. It also needs the tests. Each workflow needs the previous job. Each job in the workflow depends or needs the previous job. So in this case, it needs the workflow to pass the test job. And then next is the build and push of the Docker image, which basically calls some standard GitHub actions really to build the image and to log into ECR and to push as well, extract metadata and build and push. So from here, we also did call the Trivi scan action from the reusable repo, where the Trivi scan basically just scans the image for any vulnerabilities, any risk, and depending on what we set in the reusable repo, it should also output an artifact that can be stored in GitHub Actions as well. I don't think I remember including that. But yeah, ideally that, okay. Upload the Trivi report, okay. All right, okay, so next job would be the deployment to various environments, but that would rely heavily on Kubernetes deployment. So before we deploy in Kubernetes, we need to provision infrastructures for Kubernetes. So moving to the Terraform side of things. And okay, the Terraform provisioning code is deployed by a separate, a separate CI/CD. But first, let's look at the modules. So what we're provisioning for this project, we're keeping it really low, would be EKS, AWS EKS, the RDS, and the VPC. So looking at the structure, let's look at the structure here. Let's see. Okay, that's the architecture of our infrastructure. And what it indicates basically is one VPC with 3 public subnets and 3 private subnets. We have the NAT gateway in a public subnet for egress calls from the clusters in the private subnet. And then we have the application load balancers plugged to they are in this public subnet, but plugged to the clusters in the private subnet, and they're internet facing and receiving and load balancing the traffic, right? And then, as we know, the database is always in the private subnet, and as well as the cluster. In maybe a more robust setup, we should have a Redis cluster attached as well to reduce the hack of having to call data from the RDS all the time for caching, basically. So the Terraform, where's the Terraform module? For the EKS is, we have this, we have, well, sometimes I usually include my outputs in my main.tf, but it includes this configuration, which calls these variables, right? Sorry, these variables that are configured in, or rather declared in a YAML file. So this Terraform code structure relies on YAML declaration of values, right? The use basically is to have like a central location where values are declared rather than having several TFVAS files. So the actual provisioning is done from the resource folder, and also we also have provisioning per environment, as indicated here, the dev, prod, and stage. So if we're looking at the prod and go to the main.tf, ideally in a bigger setup, each service should have a separate main.tf, but we'll mount all of them together here. And it contains the version, the driver version, provider version, AWS, and also the S3 bucket, or the state file that takes a record of every change in the infrastructure, courtesy of this code, right? And best practice as well to keep the codes stored, the state of the code stored, and the DynamoDB as well, to prevent two modification of the code from two different engineers, and it's the provider is declared here as well, depending on this YAML declaration. As I said earlier, it actually calls configurations from this path, right? So same as the tags are called from the environment folder, and all other configurations for the EKS, the RDS, and the VPC. So what it does, if we want to look at this part, it's going to take us 2 steps back, and that will mean leaving this place to here and to Terraform, and then we'll go to environment. And for the prod environment, this is what we have. We have specific configuration per prod, which consists of values that will be picked during provisioning for the prod environment provisioning. So yeah, that's about it for Terraform. Okay, let's look at how they are deployed. That's the infra CI/CD, which begins off with, let's go faster. Okay, we're not working on the main. We didn't actually provision. This is just the code. So all necessary declarations were made, and the job starts off with detecting changed environments, and then Terraform formats and validates, and check off just like a security scan to check for any irregularities or bugs or incorrectness in the Terraform codes, and then we run the Terraform. Hold on. Okay, this is basically to detect. It's not a drift detection. It's meant to detect changes between the various environments, various environments. And then, hold on. No. Okay. So this detects the change between environments, and those actually deploys in, after scan deploys in the dev. So this workflow or this job is going to be triggered if the branch is a dev branch. If the branch that is pushed is the code push is from a dev branch and should deploy on a manual dispatch, I think same thing applies here from a stage branch and from the prod branch. So that's about it for Terraform CI/CD deployment. And we'll be moving next to, since this code should provision our infrastructure, will then be ready for deployment in Kubernetes. And for Kubernetes, okay, for the Kubernetes deployment, we are going to be using the Customize and Helm to deploy the application. Helm basically packages the application into a single package, and it's made up of the templates, which basically houses all the manifests to deploy the application, the chart for the version, and the value, which is the control file or the control of the Helm package. Now, we're not using Argo CD here, basically because it's a very simple deployment. But if we were, we would rely on the value.yaml to make changes per environment. Well, in this case, you're going to be using customize, and that's where we have the base. It basically calls the packaged application, Helm packaged application, and then deploy in overlays. These overlays are per the environment, deployment environment, which is we have dev, we have prod, and staging. So if the control here, since Argo CD is absent, the control here is basically declared in these overlays using patch files. For instance, we do have the base HPA here, right, with the minimum of two replicas and maximum 10 replicas. But if we're deploying in the dev environment, it's going to pick this this patch file for HPA, and it's going to basically change those replicas, and it's going to deploy, when HPA comes into effect during deployment, it's going to spin spin one replica as minimum and 3 replicas as max, right? And for Ingress as well, we want to look at the Ingress. It's defined in the base without a host. No host. But we look at the dev Ingress patch, that Ingress. Oops. Okay, the Ingress is internal facing in this case, which should be, I think, yes, it should. And we have the host as dev Titanic. That isn't specified in the base Ingress. So yeah, it should be internal facing, right? And then if you look at the Ingress of the prod, it should be externally facing. Okay, yeah, internet facing, yeah. And here's the host. And same thing for the staging overlay, right? So that's it about the Kubernetes deployment or coding for deployment. So in a more robust situational setup, I would use Kubernetes operators and the CRDs like ESO, especially to handle secrets that are usually in what I'm used to will be stored in Vault. But in this case, we have customized generating secrets and configurations here, right? So ideally, secrets should be handled by Vault or AWS secret manager. I'm more used to Vault, so usually I'll have the ESO operator installed in the cluster to provide secrets at runtime, secrets that are fetched from Vault, and other operators like the reloader, to ensure that rotated secrets are updated in the cluster. And for security as well, we would also include operators like or engines like the Kaiveno, to manage security in the cluster. But for this setup, it's basic, and this is what we have so far. Let's look at implementation order, so Kubernetes, and then for security, I do have this document here, doc, okay, security.md. Okay, so this is an overview of security best practices that we used in this project. For image security, we used base image, which is minimal, really light, especially for production. The node user in the Docker file, and the multi-stage build, and runtime security in Kubernetes will include all of these: security context and all tools. And then, okay, these are the reasons. And then secret management, DB password, as indicated. I don't know if I mentioned in the environment folder, environment file, variable file there, which ideally should be fetched from Vault ordinarily, right? And then, yeah, secret manager, I guess, okay. Yeah, all of this is saved in GitHub environment secrets. There should be a kubeconfig file, the Sonar token, as I stated earlier, and AWS credentials for OIDC Federation. That's in more like an organization. We log in via Federation rather than particular users, or rather than the use of static access keys. It's safer to federate into roles. Yeah. Then we have AWS Secret Manager integration with Terraform, which is stated in the infra CI/CD. Network security, network policy as in Kubernetes structure, and a database security, encrypted at rest and in transit. Yeah, okay. We also have a CI/CD security, which employs the shift left security approach, where what's it called? We have scans, have all the security best practices implemented before building the image, so better producing like a more secure image rather than building the image first and then scanning for bugs and all of those. Makes things easier. And then we do have the pipeline security as indicated here, least privileges implemented, no shell injections, OIDC for AWS as stated area, and environment production with manual approval of pro deployment. And then we have in the infrastructure security, VPC design with public subnets, have the NAT gateway and load balancer in the public, with just, with those having internet-facing capabilities and the cluster and database secured in the private subnets. The use of IAM rules as well, compliance checklists is as follows, all of this done. Yeah. Okay, so from here, we'll be moving next to the monitoring aspect, if I'm right, I think. So our monitoring structure comprises of Prometheus, the use of Prometheus and Grafana in our Latin system that uses some Prometheus rules to trigger alerts. Excuse me. So we'll start off with the pod monitor and the service monitor. The recommendation here is the service monitor for production environments. That's more secure than directly scraping metrics off of the pod. The service monitor would scrape metrics through the service, right? And that's safer for prod. And what it does basically is to scrape metrics of the application. And we do have two dashboard configurations here. This is fed directly into Kubernetes. This is directly uploaded into Kubernetes to configure dashboards. But this can be this can be used to manually import the dashboard in an external Grafana UI, or Grafana UI instance. And it includes basically, it's going to show, it's going to visualize dashboards for request weights, it's going to show or visualize dashboards for response latency, error rates, CPU usage, and memory usage, pod replicas, pod restart time. All of those contribute to latency as well, and database connections, and all those. So this file would be used to import these dashboards to, for instance, if you have your Grafana dashboard, which should be really outside of Kubernetes and needs to be viewed from time to time, we'll have to use this to import those dashboards. And then we'll move to the alerting setup, which relies on these Prometheus rules. And it contains basically critical and warning alerts, have severities of critical and warning. And we use this most of the time to prevent noise, irrelevant alerts. And the alerts groups comprise of, or the rules rather, comprise of, okay, this is critical, high error rate, that's critical. It's going to, once these conditions, what it means is once these conditions are met, an alert is going to be triggered in, say, Slack, if we decide to use Slack, other tools like Mattermost, notification tools like Mattermost, or PagerDuty, right? So it's going to notify as a critical alert, if the error rate is high, okay. Oh dear. Come on. Okay. Other critical alerts include high latency. That's a warning. A lot of warning severity. High CPU usage. That's also a warning. High memory. And all those database connection errors. So that's the alerting setup. And for documentation, we're basically looking at this, which we might have gone through. We also do have a README here. The documentation is quite more detailed, than the README. The README is a summary of what I did. Pardon me, my mouse is acting up. Okay, so this is a summary of my work so far. The CI structure and the deployment in the Kubernetes cluster. Ideally, we didn't use the CloudWatch. We didn't use the ECR here for the secret manager, but this would be the case in a more structured AWS provider, cloud provider architecture. These are cost estimates, per environment, and okay, I didn't talk about disaster recovery. That is specified in the deployment, where we have that's not disaster recovery really, but in the app deployments, we do have a rollback job. Should, in case a deployed version isn't stable, we do have this job in place, and it specifies let's go down. It does specify okay, it's going to be a manual deployment, and it's going to trigger only if it's a prod. GitHub include rollback. Okay, if the action is a rollback action, and let's see. Oh, yeah, so okay, so this will trigger a rollback to a previous deployment, the very previous deployment, if a particular deployment is not stated by the workflow. All right, and it's going to send a notification to Slack. Now, this is made sure of in our Kubernetes deployment in the base, starting the base, yeah, where we do have revision history limit. So we do have, like, it keeps a record of or a history of 10 previous deployment histories. So if a rollback is automated or manually triggered, if a particular deployment number isn't specified in this CI, it's going to roll back to the last stable deployment. So for disaster recovery, back to disaster recovery, what we do have, no, that wasn't here. We do have the RDS, which caters for automated backups of data, and the fact that we also have multiple availability zones caters for recovery should one go down. EKS declarative IAC Terraform rebuild, application container image in the ECR, which can always be sourced, or recovered for any rebuilds and all those. And then we have secrets managed ideally should be managed in Vault or the secret manager. So yeah, that's about it for this project. Just going through. Okay, I did also plan to include some images and point to them. But just to go over what should be in the task, just briefly running through. Oh, this 47 minutes already. Pipeline efficiency. Yeah, the project caters for pipeline efficiency, error handling, and recovery. Recovery. Yeah, we rollback. For observability, observability maturity. This is catered for a single microservice. Alert quality, yes, to increase the noise, we focused more on the critical alerts of severity, critical and warning, which are most important and should alert SRE on call engineers to action. Dashboard usefulness, that's Grafana dashboards. Infrastructure, we do have code organization and modularity is in place. Security posture, yeah, in place with the checkoff scan and secret handling. And cost optimization, here we trim down to just a few services since it's a single microservice deployment. And yeah, it's scalable based on the use of the YAML variable declaration, which can be easily edited and increase or reduce services. And then security and compliance, we do have a robust defense in place with the shift left security approach. Secret management, and which we have secrets stored in GitHub Actions, secrets, and compliance awareness as stated in security doc. And then for evaluation, for disaster recovery, as we stated, we have backups, we have we have data backups, we have the use of various availability zones, for recovery in case a particular availability zone goes down. We also do have a documentation clarity to effect this to ensure that recovery time is in place and together with the right objectives. I think I left one out. That would be, let's see. For Kubernetes high availability, yes, we do have clusters in 3 different subnets for high availability and production readiness. For the containerization and local development, we do have the image optimization and security in place, where we have the app user and ensure is a low memory image, and then development experience, how easy it is to run locally. Yeah, it was quite easy to run to view the image and the Docker Compose deployment locally. And then we look at documentation quality as well. That will be in my solution with MD5. But one thing I want to also specify here is in the app CI/CD. If you see, I have the unit tests commented out here. This is because my build, my workflow was failing these points. It failed the unit test, and I did try to fix the source code, the Python source code. I did a lot of back and forth, on the GitHub default runout, looking at the actions. But rather than waste time, I decided to comment those out and continue with my my CI/CD, and maybe I'll include a picture of one of my builds. This is the last. Let's see if we get to see. Yeah. So I see okay, this is the last push. Okay. Okay. It actually failed at this point. However, my initial commit had the check of, let's see here. Let's see. Yeah, it did pass the Chekhov scan job. So I had a lot of issues at the unit test, did several fixes, but it took too much of my time, and I decided to let it be. Where are those? Now those are the commits. Unit test fix, unit test fix, unit test fix, unit test fix. Okay, at this point I said, okay, I'm leaving it for the devs you know. So that's it about my project, my Titanic DevOps assessment project, and it was actually a wonderful experience, and my takeaway from this would be, the importance of understanding the AI. It's one thing to understand or to know your tools, know what you need to know as a DevOps, but it's another thing to also deliver within the time frame, to deliver with speed, and that's where the AI come. And this has enforced or sort of, uh, strengthened my decision to continue my AI knowledge build. I recently enrolled for some courses, generative AI, agentic AI on Udemy, and well, I need to go back to them, and complete them. So that's it for this project, and thank you for listening. Cheers.